So far, we've talked about addition reactions where there's only one double bond that will react. Some of our reagents have had benzene rings in them, but remember those are unreactive towards addition. But what would happen if we have a conjugated diene? And let's go with the shortest one that we can do, which is butadiene. 1,3-butadiene. So in this case, we've got two choices, or two double bonds that we can add to. And we're going to explore 1,2 addition and then also 1,4 addition. So let's go ahead and draw the products of each of these, and then we'll talk about how this works. So I'm going to add HCl to this, and let's do 1,2 addition first because that's adding on just across one bond, and it's called 1,2 addition because it happens 1,2 carbon. They're adjacent carbons. So when we do that, we'll leave this first one alone. We'll just do the attacks on this double bond. No particular reason for that choice, since this is a symmetrical molecule. And this would be the product of 1,2 addition. Now, what's 1,4 addition? Well, 1,4 addition will put the addition on the one carbon and then on a carbon 4 away from it. So 1, 2, 3, 4, 4 away. And that's so-called 1,4 addition. And this is interesting because the double bond moves in this case. Now in 1,2 addition, notice that the double bond is in the other double bond is in the same position that it started out as. In the 1,4 addition, it has moved to a carbon that, between carbons that initially had a single bond. Now those carbons have a double bond. So let's look at the mechanism and we can explain this process. So first, we're going to protonate this bond right here. So we'll have to get our HCl, we'll do a protonation step. Now, we're going to want to have the positive charge end up right here, because if we have the positive charge end up there, first of all, we're violating Markovnikov's rule, but really the main reason is we don't want to make a primary carbocation. And then you'll also see that there are some stability gains in this case. Okay, so this is what we're initially going to form, right? The positive charge is here, it's on the secondary carbon, just like typical. Now, if this one reacts with a chloride, and we have a chloride come in, we'll make the 1,2 product. So this one could lead to the 1,2. And I'll just draw that here. Leave a little space. So that comes in, attacks the plus charge, and then makes the 1,2 product. But there's a resonance structure for this one. All right? So we could take this, move that over, and then the plus charge ends up over on the other carbon. And the double bond moves to there. Now the plus charge is out on this carbon. And you might say, ooh, that doesn't look so good. It's a primary carbon. But remember, this is part of a resonance structure. And so this is actually quite stable. And we have the di-substituted double bond. And the more substituted carbons that we get around a double bond, the more stable it is. So this is actually the more stable of the two resonance structures. And then in this case, if we have a chloride come in and do an attack, on that carbon, we can make the 1,4 addition product. And so that's the mechanism of how this works. And if we're going to have either 1,2 or 1,4 addition, we will need to have these conjugated or double bond, single bond, double bond, like that. Now, you might be asking, how do we control which way this goes? Because maybe I would like the 1,2 addition product. Well, how do I get the 1,2 addition product? Well, that is the kinetic product. So I'll have to set up kinetic conditions. That is lowering the temperature and in having the attacking species at a very high concentration. What if I want 1,4 addition? Well, this is thermodynamically more stable. And so if I increase the temperature of my reaction, then I can promote the 1,4 product. Now I'll still get both during this reaction, but I can change which one will be the more predominant species. Okay. So in this case, since the 1,4 is more substituted, this is the thermodynamic. And we can promote that by having higher temperatures. Now, if we want the 1,2 product, this is the kinetic product. We'll look to make this using lower temperatures. Now, I explained that since this is the more substituted double bond, that this is the more stable one. And that makes this the thermodynamic product. How is this one the kinetic product? Well, let's just draw the transition state here again, just to help out. So we've got our double bond right here. And I'm going to go ahead and draw my hydrogen and my chloride right here, just like this. And then I can have that protonate there, and that will make the proton attach right there. And I've got my chlorine right here. And at a lower temperature, molecular movement is a lot slower. So I'm going to have my chloride right ready for when that plus charge happens right there. So I'm going to just draw that in right here, and I've got my proton on that carbon somewhere, and my chloride is positioned right ready to attack that right away. And so since this chloride is very close to where that plus charge is formed, kinetically this can be a little bit faster. Now, that isn't to say that we will always have 1,4 addition be the thermodynamic product and 1,2 be the kinetic. In many cases like this, that is true, right? 1,4 is the more favored and 1,2 is the more stable one, so that's the thermodynamic one. But that isn't always the case. Sometimes the more stable product is the 1,2 addition, and that tends to be always the kinetic product. And so in those cases, we would greatly favor 1,2 addition, because no matter which it is, higher temperature or lower temperature would make the same product. So you'll just have to play around and look at the other resonance structures that you can form. And if there is a more favored resonance structure that results during the 1,2 addition, then that would also be the thermodynamic product. But like I said, in this case where we have this simple one, we do have a clear delineation between the two options.